Semiconductors come in two different types. Semiconductors are, as the name suggests, materials that kind of conduct electricity. They're not conductors in the normal sense of, like, metals like gold and copper and silver, but they're also not insulators in that they do allow electricity to pass through them. Things like insulators have all their electrons locked into their atoms, so they can't use those to transfer energy like electricity around. But semiconductors use the addition of two different types of elements to basically create a similar effect to what you get in conductors. So silicon is really the basis for all semiconductors, and you've got silicon over here in group 4. So this is group 4 here. So group 4 means that it's got 4 outer electrons, so 4 outer electrons that can bond to other types of atoms. Now, what you can do with semiconductors is you can either add a group 3, maybe one atom in every 1,000 or so can be changed to something that is in group 3, or one atom in every 1,000 or so can be changed to something that is in group 5. So that means you either have one additional electron or one sort of missing electron. So if this is silicon, if this is our silicon lattice and it is joined together, because that's how non-metals bond together, they bond together covalently. If there are 4 outer electrons, then you get 2 silicon atoms that are immediately adjacent to each other, then you're going to get this sort of effect where you've got all the available holes being filled with electrons. However, if you then attach that to something else, something from group 3, so it could be boron, it could be aluminium or indium or any of these elements in group 3 here. Group 3 have 3 outer electrons, so therefore you actually end up with something that looks like this. So instead of having an electron there, we end up with what we call a hole. Now, a hole is basically a positive charge. It's the absence of an electron. So you've got this hole here that comes from this group 3 element. Let's say it's just aluminium, just to put a name on it. There's this hole, and electrons like to move into holes because it's like negative and positive charges being attracted. So what you end up with is a little negative charge that can move around. So you might have a negative charge over here, and it might see that hole, and it will pop into that hole, and it will leave another hole behind it. So you basically get the movement of a hole around this crystal lattice here, which is why it's called p-type material. So this is p-type material here. And p-type material you basically create when you add something from group 3, so you've got an extra hole, and it creates this movement of a hole, which is basically created by electrons moving around. If we do the same for the other type of material that can make up semiconductors, say we start off with silicon over here, it's got those 4 outer electrons, it bonds covalently to another silicon atom over here, and that just repeats itself. If we then bond that to something that is in group 5 here, so it could be phosphorus, for example. We put phosphorus in there, so it's got 1 extra electron, so it fills up all the levels here as silicon would normally, but it's left with 1 sort of extra electron that doesn't really have anywhere to go. So that extra electron can then move around this lattice. It can go about the crystal lattice there, and it can carry electricity that way. So it's a negative charge carrier this time, an electron rather than a hole. So this is n-type material. In both of these situations, what you're doing to the insulator that is silicon is effectively reducing its resistance, and as you reduce its resistance, it means it can carry electricity more easily. So that's your 2 types of material, p-type and n-type. P-type is holes that carry the electricity, n-type is electrons that carry the electricity. So it's all to do with which impurity you add to the silicon. You grow that as a crystal, and generally what they do is they grow p-type and n-type material together, and they create something that we call a p-n junction. And a p-n junction is just really 2 types of material together, so you end up with On your left hand side there, holes, which is basically the absence of an electron, and then on this side here we get electrons. So one side is negatively charged and one side is positively charged. When you originally put those two things together, then you get electrons going to fill holes, because that's what electrons do. So all of these electrons jump over here, and you end up with something that looks like this. So if we skip out all the other stuff, then these electrons have moved over here. So we've got a line of electrons here, and then we've got a line of holes here where those electrons have left, and then we've got holes all over this side, and we've got electrons all over this side. So what you end up with there is a bit of a stalemate, because if we take this on its own, these little electrons here, they don't want to go back over to this side. These holes here, they don't want to go back over to this side, so you end up with no conduction at all. And this is what we call the depletion layer. So at this point in the p-n junction, although the p-n junction will ultimately become, as we'll see, the basis for most modern electronics, it can't really do anything at this stage when you stick them both together, because you've got no conduction going on here. So you've got to do something in order to make these charges begin to move again. And that's when you create something that's either forward bias or reverse bias. So we connect it to a battery. So we've got p-type material, our holes here on the left hand side, and n-type material, our electrons on this other side. So forward bias is, as it would suggest, it moves things forward. Reverse bias moves things in reverse. So if I want to move holes and electrons together, then I'm going to have to repel these positive charges or attract these negative charges this way, and I'm going to have to push the negative charges this way or attract the positive charges that way. So that tells you how to connect your battery down here. Now I'll do it this way first of all. That's positive and negative there as a battery. That's forward bias. So this positive terminal there attracts. You can think of it as attracting these electrons this way. You can think of this negative terminal as attracting the holes this way, or you can think of it as the positive terminal pushing the holes this way, or the negative terminal pushing the electrons that way. Either of those is acceptable, but you don't have to necessarily remember. Some people struggle with remembering which one is which. So you can actually use just a standard symbol. Reverse bias does the opposite. I'll do this in a different way. Reverse bias pulls these things apart. So you want to attract this around here. So your negative terminal's got to be there, and then your positive terminal has got to be there. So it attracts electrons around this way, attracts holes around that way. So what this does really is pushes things together. And what this does is it pulls things apart. But both of them have uses in electronics. You can use this symbol or that symbol incidentally. Forward bias, for example, is the basis for photodiodes, how diodes work. Diodes basically only allow current to flow in one direction. So you can see there that it will only allow current to go in one particular direction, the direction that allows these holes to join with their electrons. If it doesn't, then you won't get current flowing. That's the basis for solar cells, LDRs, for example. Speaking of diodes, you can have two different types of diodes. You can have a photoconductive mode. For a diode, that's when you basically use it to conduct, like in this particular way here. You can that's when it's connected to a voltage supply. So it only allows current to flow in one particular direction. So it could be an LED, or it could be something like that. That's your photoconductive mode. Photovoltaic mode is when it's actually used to generate electricity. So instead you'll have photovoltaic mode is when you use something like this to actually generate some sort of electricity. So in photovoltaic mode you won't be connected to any sort of voltage supply. You know, you will have some sort of voltage output there. So a solar cell works in that way, and that's reverse bias that uses that. So if you're pulling like the holes and the electrons further apart, then you create this bigger depletion layer than we saw earlier with the depletion layer in the p-n junction. And the only way you can conduct is if you shine light on that depletion layer. If you shine light on that depletion layer, then it basically makes electrons and holes combine and produce energy in the form, in various forms. So photovoltaic mode and photoconductive mode, forward bias and reverse bias. You've got to be able to identify all of these. So learn them and know what they are. Right, on to the sort of questions that you can expect to get on this. So the light gate consists of a lamp shining onto a photodiode. The photodiode forms part of the circuit shown. In which mode is the photodiode operating? Well, I would look there for a power supply or not a power supply. There's a power supply there, so there's conduction. So it's photoconductive mode for that particular one. Photoconductive mode. Explain why the timer only operates when the light beam is broken. Well, when the light beam is broken, that means that you can basically say goodbye to the light that's hitting on this. So at that point in your p-n junction, you've got this big depletion layer, and there's no light falling on that, so therefore there's no electrons and holes combining, there's no conduction at all. So because there's no conduction, that makes the voltage across this part go up, because you can think about it as resistance, you know, becoming a maximum value. So therefore voltage goes up, and that voltage goes up above, you know, the 2 volts that is required to switch on this MOSFET, and that causes the timer to operate. Remember the MOSFET as well, we've got gates, we've got 3 parts to that you need to know. Gate, source and drain. I won't go through the MOSFET, but remember that it is another type of semiconductor, and it has a different arrangement of P and N type materials within it. Next question. A sample of pure semiconducting material is doped with impurity atoms, like I was talking about at the start. How does this addition affect the resistance of the semiconducting material? Well, it reduces the resistance. So it basically allows current to flow through where it wouldn't have been able to flow through before. So it's a reduction in resistance, like I was explaining at the start. Here is more what I was looking to get onto with this question. You've got a p-n junction diode there used as a light emitting diode, so it's the basis for LEDs, used commonly nowadays. Explain in terms of the charge carriers how the LED emits light. Well, you've got your N and your P there, and somehow that emits light, so you've got to be able to explain why. And the basics behind it is that from this side you're going to get a hole, from this side you're going to get an electron. Those electrons and holes combine together at the junction to release a photon. It's just to do with, you know, how close to the surface this particular layer is, whether it, you know, it emits light or not. If it's quite close to the top of the semiconductor material, then it causes it to emit light. It's just a property of semiconductors. So you get holes and electrons combining here at this junction, releasing a photon, and we see that photon as a certain colour of light. So electrons and holes combine at the junction to produce a photon of light. That's your basic sort of answer there. Here is something slightly different down here. Maybe just go through it because it's something that people do struggle with. Remember, when you've got anything like that, a diffraction grating, then it's n lambda equals d sine theta. You'll find that equation in your formula booklet. N is your order of the maximum or minimums here. It's maximum for this because it's n lambda, so it's 2 lambda. D is your spacing between the lines on the diffraction grating, which is 5 times 10 to the negative 6. Theta is your angular breadth, basically the angle that the maximum hits at from this central maximum, so that's sine 11 degrees. If you solve that for lambda, you'll find it's 477 nanometers, so in the visible range there towards the blue end of the spectrum. One more semiconductor style equation. Copy the diagram and add the battery so that the PN junction is forward biased. So forward biased is when it's driving the two together, and you can do this with a battery symbol or you can just do it with a power supply symbol. It's probably easier to draw it like this. You've just got to get your positive and your negative around the correct way. So P-type, you want to repel that P-type and attract this, so this is going to be positive, which leaves negative for that. So that's what you would draw for that, and that would get you the marks. Using the terms electrons, holes and photons, explain how light is produced at the PN junction of an LED. Very common question, as you can see. Electrons and holes combine at the junction to produce a photon, which we see as light. It's the same answer as the previous one. So it's all about electrons and holes combining to release energy in the form of a photon. This second part here, part C, leads us into our next wee section, which is on optoelectronics. So calculate the wavelength of a photon of light from this LED if the photons of energy that are given off from here, if those photons have energy 3.68 times 10 to the negative 19. Calculate the wavelength. So what we need to do first of all is do E equals HF, because the energy that a photon has is directly proportional to its frequency. So although a photon is a particle, it's not a wave. Remember, they are tied together. They also have, the photons have a frequency and have a wavelength associated with them. So this is 3.68 times 10 to the negative 19. And that's equal to Planck's constant multiplied by frequency. Planck's constant you'll find from your datasheet at the front of the higher paper, multiplied by F. So you get a value of frequency that is 5.55 times 10 to the 14. You can then do B equals F lambda, because you know that all photons travel at the same speed. They travel at the speed of light, 3 times 10 to the power 8 meters per second, is equal to 5.55 times 10 to the 14 lambda. And lambda will give you 540 nanometers. So again, in the visible range of the spectrum. Calculate the minimum potential difference across the PN junction when it emits photons. Well, minimum potential difference that's going to be produced is going to be from one singular electron, which has a charge of 1.6 times 10 to the negative 19 coulombs. You'll find that again in your data sheet. This is your energy, so it's related together in this equation back from using electricity. It's W equals QV, where it's 3.68 times 10 to the negative 19 is equal to 1.6 times 10 to the negative 19 V, and you'll find that V is 2.3 volts. So that's the minimum potential difference you'll produce, if you've just got one singular electron. So this E equals HF, that becomes very important, particularly when we're doing the optoelectronics side of things, which is what we're going to now. This ties in quite closely with the whole semiconductor idea. You've got photons here of a certain energy striking a surface. When you shine light upon a surface or any sort of radiation upon a surface, it gives out electrons. That's just a property of nature. But these photons need to have the correct energy. Every material has a work function, which we can call WK, and that work function is the minimum amount of energy that's needed in order to liberate these electrons from the inside of this material to the surface here. So if you put in an energy that from these photons, say they have energy E, if you put in just the right amount of energy that matches up with this work function, you will get this electron being liberated to the surface there and nothing else. If, however, you put in more energy than is needed for the work function, then any remaining energy will be as kinetic energy. So the energy of our photon, just as with the previous question, is E equals hf. So that gives us the energy that the photon has. The work function here is related, the energy is related to this frequency, the threshold frequency, hf naught. And then anything that's left over is as kinetic energy here. So your energy, your kinetic energy, is essentially equal to the energy that the photon has up here minus the energy that it gives up to the material to cause the electron to be ejected there. And we call that photo emission. You know, this is photo emission. So the photo part comes from the light, that's just really another word for light, and the emission part is because the electrons are given out. So we use this material, you know, this sort of technology to explain things like the photoelectric effects. Doesn't matter how many waves you put in, if they're not of the right frequency, then you know they won't cause photo emission to happen. And that was the basis for figuring out that maybe light isn't a wave, maybe it's also a particle. And we find that it is that case. You know, sometimes light acts as a wave, and sometimes it acts as a particle. That's what we call wave-particle duality. This can only be explained by thinking of light as being a particle that we call a photon. So it's like one photon per photoelectron. So one photon gives up its energy to this electron, it's going to cause it to be liberated. But how much energy that takes is dictated by this thing, this work function. Any leftover energy is given as kinetic energy. That can only be explained by this particle theory of light, by the fact that, you know, that light is photons that have a certain frequency. The amount of energy a photon has is directly proportional to its frequency. So unless you've got the exact right frequency, then you don't have the right amount of energy and you can't make photo emission happen. Okay, one last question, and then I'll let you work through the ones that I've given you. Ultraviolet radiation from a lamp incident on the surface of a metal. As we just discussed there, if you put radiation onto the surface of a metal, it will cause electrons to be liberated and to move away from the surface, but only if the energy is right, only if the frequency of those photons is correct. The energy of each photon of ultraviolet light is 5.23 times 10 to the negative 19, and the work function is given there. First of all, calculate the maximum kinetic energy of an electron released from this metal by this radiation. So that will be 1 mark there. That's your energy of the photon. That's more than this value of the work function. So there's going to be a certain amount of energy left. That energy is kinetic energy. So your kinetic energy here is 5.23 times 10 to the negative 19 minus 2.56 times 10 to the negative 19. That will give you 2.67 times 10 to the negative 19 joules. Part 2. What's the maximum speed of the emitted electrons? This is a wee bit different. This is using half mv squared. Ek is a half mv squared. You know that Ek is this value here, 2.67 times 10 to the negative 19. A half multiplied by mass. You don't have mass, but it's the mass of an electron. You're just looking at one solitary electron. The mass of an electron, like the charge of an electron, is given in your data sheet at the front. That's 9.11 times 10 to the negative 31 kilograms. And now all that multiplied by v squared. So v squared comes in at 5.86 times 10 to the 11, making v 7.7 times 10 to the 5 meters per second. The source of ultraviolet radiation is now moved further away from the surface of the metal. State the effect, if any, this has on the maximum speed of an emitted electron and justify your answer. Well, this is really a question of irradiance, and irradiance being, you know, the number of photons basically that's fallen on the surface area of this particular material. It's power per unit area. There will be less photons because you've moved this further away. Remember that irradiance is the equation that you get is K divided by D squared, which basically means that the irradiance, the intensity effectively of the radiation reduces by the square of the distance as you move away. So you've got less photons falling in here, but these photons are still of the correct energy, they're still of the correct frequency. So that's what dictates what the kinetic energy is here. The work function is still the same. The work function is unchanged. So it's going to give up the same amount of energy to get this electron to here, and then it's going to have the same amount of energy left to cause these electrons to move away there. So the answer here is that the maximum speed of the emitted electron is unchanged. The only way you can change the maximum speed of that electron is if you change the energy of this incident light here. There are less photons falling on there, so it would reduce any current that you were looking to produce, because there would be less photons, so therefore less electrons produced. But it's not going to affect the maximum speed here. Maximum speed remains unchanged because the energy of the ultraviolet radiation is unchanged, the work function of the metal is unchanged. So each electron that is emitted will still have the same kinetic energy and therefore the same maximum speed.